Hi, in this video we will learn what is transpose of a matrix, what are the properties of transpose, and we will introduce a class of matrices called symmetric matrices. Let us start with the definition of the transpose. So let A be an n by m matrix. Then the transpose of A, well, we have a notation for that which is denoted by A transpose. The transpose of a matrix is a matrix. So you see the original matrix A had n rows, m columns. A transpose is the other way around. A matrix with m rows and n columns. So in other words, A transpose is m by n. The second thing is that, okay, so the rows and number, the number of rows and columns changes. It actually, the whole rows turn into the columns. So in other words, the ij entry of A transpose is ji entry of A. So you switch row 1 to column 1, row 2 to column 2, row 3 to column 3, and so on. That is the transpose. Well, let's just see in a few examples. These guys are here. Okay, we have a transpose of square matrix. It's 2 by 2, so the transpose will be again 2 by 2. So 1 entry here goes to 1 entry. 1 2 entry, however, 1 2 goes to 2 1 entry, so it will be here. 2 1 entry goes to 1 2 entry, and 2 2 entry goes to 2 2 entry. Or all these things can be seen in this form. Switch the first row to the first column, the second row to the second column. Here you started with 2 by 3, now we have 3 by 2 matrix. How about this guy? This is 3 by 1 matrix. Now you transpose the first column goes to the first row, and this is 1 by 3 matrix. This operation, as you see, this is very easy operation to do, but it has very nice implications in matrix theory. Well, let's see properties of this transpose. First property says that, well, transpose of transpose is the original matrix. So if you first turn rows to columns, then do this again, so you turning the rows now back to the columns, you will get back A itself. In other words, if you have A transpose of transpose ij entry, you will have A transpose ji entry, and then another one ij entry. So ij entry of A transpose is ij entry of A itself. That means that A transpose is equal to A. Okay. How about transpose and addition? So if you have A plus B transpose, what do you do? Okay, so we have A plus B, look at, oh, transpose. Look at ij entry. Ij entry of the transpose is ji entry of the matrix, yes. But this guy is the same thing as AJI, well, let me write it in lowercase here, plus BJI. But this is the same thing as A transpose of ij, yes. So you find transpose and find ij entry, and then this is B transpose of ij entry. Now that we have both ij entry, you see that this means what? This means that A plus B transpose is the same thing as, let me complete this proof, A transpose plus B transpose. Look at entry ij. So here, yes, A transpose plus B transpose. So transpose expands nicely on the matrix addition. How about scalar multiplication? Well, I will leave this one to yourself. This is, you multiply each entry by k and then switch the rows with columns. It is still each entry of the transpose multiplied by k. Well, k is a number, yes, here k is a scalar. How about matrix powers? Well, matrix powers also works nicely with the transpose. So if you have a to the power r, then transpose, it will be the same thing as you find the transpose first, then find the r, power of r. And the last property is the most important one. It says what? It says that what happens, what is the relation between the transpose and matrix multiplication? And this you have to keep in mind. A B transpose is not A transpose B transpose. It is the other way around. It's B transpose A transpose. And why is that so? Because if you start with a B transpose, look at ij entry, because the transpose, ij entry of the transpose is ji entry of the matrix itself, but ji entry of the product is row j of A dot column I of B. But we know that row J of A is same thing as column J of A transpose. Yes. Dot, this is and column I of B is row I of B transpose. Well, dot product is commutative, so you can have this dot column J of A transpose, and now row I of B transpose dot to column J of A transpose. This means that we have the ij entry of B transpose times A transpose. This is the important property that you should keep in mind. Okay, so let's use these properties and do an example here, which is solving a matrix equation for x. Okay, so we have this matrix here, a matrix equation. Now we want to solve. There is a transpose up there. To get rid of this transpose, because we want to isolate this x, yes, so we have to get rid of that transpose, you can do several things, but one of the things that I like here to do is that to get rid of transpose, apply transpose another time, because transpose of the transpose is the original matrix. Here, however, we have two sides, so we have to put both sides to the find transpose of both sides. Okay, transpose of transpose is the matrix itself. So here, let me multiply this inside. 2, negative 2, 4, 2. This guy, however, you see, this is A, this is B. A, B transpose is B transpose. So this is B transpose times A transpose. But A itself had a transpose here, as I defined it. Now, the transpose of the transpose, this guy is equal to 1, negative 1, 2, 3, 1, 0. Transpose of transpose is the original matrix, which is this guy here. Let's find the right-hand side and then apply what we have here. So the transpose of this is 1, 2, 1, negative 1, 3, 0. This is multiplied to 2, 1, negative 1, 0, 1, 1. And the result of this, you matrix multiplication. 1, 2, 1 times 2, negative 2 plus 1. This is 1. This guy multiplied, 1, 2, 1 multiplied to 1, 0, 1. This gives us 2. Negative 1, negative 5. This guy. And this will give us negative 1. So our equation is now x plus 2, negative 2, 4, 2 equals to 1, 2, negative 5, negative 1. Add both sides with the negative of this. In other words, take this to the other side. That's what it means. But we have to turn it to negative, or add addition by its negative. And this gives us the solution for the equation. 1 minus 2 is negative 1. 2 minus negative 2 is 4. Negative 5, this is negative 9. And negative 1 minus negative 2 is negative 3. There are other ways, as I said, to solve this equation, but I like this method because you see how the properties of matrix come in. Okay. Some of the matrices, when you find the transpose of that, you get back the same matrix. These kind of matrices called symmetric matrices. So definition: a matrix A is called symmetric if A transpose is equal to A. While one thing to note here is that every symmetric matrix is square matrix, isn't it? So every symmetric matrix is a square. It's a square matrix. Why is that so? Because A transpose is equal to A. That means the number of rows of A is equal to number of columns. That's what it means. Well, what are the examples? The examples are something like, well, if it is 2 by 2, you can have anything on the diagonal, main diagonal, and you can have anything up diagonal. Let's say 3 here. But everything below the main diagonal, which you should repeat what you had up there. So this is the transpose of this matrix is equal to itself. Or you can have something like 2, 3, 4, and then up there you whatever you like, 1, -2. But then everything down here, so it considers reflection with respect to main diagonal, you should get the same number. So 0 here, 1 here, and -2 here. So the question comes up, well, what are the good examples of, or how you can generate good examples of symmetric matrices? There are actually very good facts about these things. So let me just write these as theorems or facts. If you have a matrix, any square matrix, for any square matrix A, you can make a symmetric matrix using this A. The matrix A plus A transpose is symmetric. Why is that so? Why? Well, if you want to check something is symmetric or not, you have to find its transpose and show it that it is equal to original matrix. Here, the transpose of A plus A transpose, you know that the transpose distributes over the sum. But the second summand already had a transpose. So this is transpose of transpose is the original matrix. And we know that the sum of matrices or matrix addition is commutative. So we started with A plus A transpose, and we showed that it is equal to A plus A transpose. That means that A is symmetric. So that was the first fact. That's when the matrix is square matrix. What happens if matrix is not square? You see that if matrix is not a square matrix, you cannot add A to A transpose. But still, you can find a way to make a symmetric matrix for any matrix B. The matrices B transpose B and B transpose are symmetric. So it means that you multiply the transpose of any matrix you like to itself, you will get a square matrix, either from left or from right. Doesn't matter, you will get a symmetric matrix. So why is that so? Again, so to check something is symmetric, you have to find its transpose. And we know that the transpose and multiplication works nicely, but you have to change the order. And the second one is transpose of transpose. So we started with B transpose. We ended up showing that this is equal to B transpose B itself. So that means that BTB is symmetric. You can do the other one, also has very similar proof. The only thing here is that you see the transpose of AB is B transpose A transpose. This is why this guy comes first and this guy, transpose of this guy, comes second. You just multiply any matrix to its transpose from left or from right, you will get a transpose matrix. These were just basic properties of transpose and the symmetric matrices.